Hello, this is the Week 1 lab for Physics 2212. So as a quick overview, this lab is about using electric principles to approximate the excess charge on an object. This is done using the concept of electric fields and the charging of everyday objects. The purpose of this lab is to visualize the effects of electric field around us by using something that is small, easily observable, and readily available, which in this case is a piece of tape. So a big part of this experiment is our use of U-tapes. A U-tape is a charged piece of Scotch tape with handles on the end for handling. And as far as the interaction between two pieces of U-tape, they should repel each other as they should have the same charge if they were made correctly. This is my expectation, and it was proven correct upon trying it out for myself. As far as determining the sign of the U-tape, you can actually do this with a plastic pen. If you rub the pen through your hair, it should pick up electrons and become negatively charged. If it's attracted to the U-tape, which you know is charged, that means it will have a positive charge. Likewise, if the U-tape was negatively charged, it would have repelled the pen, which I know some of my teammates experienced, but I personally did not. And if the U-tape was neutral, perhaps you handled it a little too much, it would still be attracted to the charged pen as the tape would become polarized. Now let's imagine a scenario where electrons were suddenly positive charged and protons were now negatively charged. All the electric interactions we observe would stay exactly the same, as all that really happens is that the sign of the charges would flip, which means that all objects that were once attracted to each other would still be attracted to each other, and those which were repelled to each other would still be repelled to each other. I mean, in the case where you bring a charged object near a neutral object, there would still be an attraction as the neutral object would still become polarized. So essentially nothing changes. So this is actually a picture of my setup for this experiment. I opted to use shoe boxes instead of books. An important part of handling the tape is that you really want to touch it as little as possible. This is because when you do touch it, you're actually slowly discharging it by allowing it to disperse its charge through your body, and you're really just making it weaker. As far as excess charge on the U-tape, we can deduce that the electric force and the force of gravity on the tape have to be equal, since there is no change in momentum of the tape B, or the upper tape. This is my free body diagram for the tape on the left. As you can see, the only two forces acting on the tape are the electric force from tape A on B and the force of gravity downwards. And on the right side, I have my mass calculation for the tape as well as my force of gravity calculation using the given tape density of 1 gram per meter. So using our measured values for the mass of the tape and the separation of the tape when it starts levitating, we can actually find the amount of charge on the two pieces of tape since they're approximated to be the same. This is possible due to the fact that we know that the magnitude of the force of gravity and the magnitude of the electric force of tape A on tape B have to be equal. As a result, we can rearrange the two formulas to give us a value for the charge of the two tapes, which in this case was 1.189 times 10 to the negative 8th coulombs. And since we know the charge of an electron and we know the charge of the tape, we can find the electron deficit by simply dividing the charge of the tape by the charge of an electron and giving us a 7.429 times 10 to the 10th electron deficiency. We can actually approximate the total number of atoms in our piece of tape by dividing the area of the tape by the area of an atom. In the case of my 24.5 centimeter long piece of tape, I had roughly 4.9 times 10 to the 17th atoms. Using this number, we can actually calculate the ratio for the electron deficit to the total number of atoms, which in this case was 1.516 times 10 to the negative 7th. So as far as assumptions and approximations in this experiment, we approximated the strips of tape to be perfectly square when we were finding their area. We also approximated the charge of the entire strip to be concentrated at the center, which is really rough to make. We assumed all strips of tape to possess the exact same charge despite them having different lengths, and of course all measurements are approximate as our eyes are only so precise. This is actually a screenshot of my glow strip code for this lab. As you can see, I use spheres to represent the top and bottom pieces of tape respectively. The orange vectors represent the electric force vectors, and the green vector represents the force of gravity on the top piece of tape. Also, in the text box, I've also given the user all of the information they need to double check my work if they want to, including the length of the top piece of tape, its density approximation, as well as the locations of the two spheres. But I do also give them the necessary charge to make the top piece of tape float above the bottom piece.